Hi there, welcome back to part B of the solubility equilibrium videos. So in part A, we learned how to write equilibrium processes for a solute dissolving into its ions, and the properties of that as it interacted, and how to determine the maximum solubility of something. So now we're going to take it one step further, and using that as a property, we're going to look at reactions in which precipitates form and the limit at which they can be done before those precipitates form. So up until this point, we looked at solubility of solutions with one ionic compound. Okay, not one ion, one compound. Now we're going to look at what happens when we mix two solutions and consider all the interactions between everything. You see a nice diagram of this in your textbook. So to start off, we'll do with an example. We'll write the reaction that represents the mixing of NaCl and AgNO3. So, NaCl, right, because they're being mixed, they're aqueous solutions. All sodium and nitrate compounds are soluble, right, and will form a precipitate here. And again, that's based on your solubility series plus NaNO3. So these are double displacement reactions. The positive ions switch places, right, and we check their states on the new one. So that's balanced. Now, because this forms as a precipitate, we know that in solution, so that's reaction A, as soon as that forms in a beaker, some of it will start to dissolve. Right? And things dissolve according to equilibrium. So we'll have aqueous. So even though that precipitate is insoluble, small amount of it will dissolve. Right? And those are all balanced because it's all a 1-to-1 ratio. So keep this in mind. Whenever we see precipitates forming, they don't just sit there on the bottom of the beaker. Right? So if we have our beaker here, right, small amounts of it are dissolving, and then small amounts of it are recrystallizing. So it looks like there's no change, but there's that dynamic equilibrium going on in the background. So precipitates don't just sit there, they're actually conducting their own process. So we talk about this here, right? And the formation of the precipitate depends on the equilibrium concentration of the ions in the solution. So in some cases, if we do a double displacement reaction with really dilute solutions, which have low concentrations, then the precipitate won't form, even though we expect one to. So there has to be a threshold for concentrations that will let us see the precipitate. So what happens is when they mix, these ions become diluted and their concentration goes down because initially you had a beaker in the previous example of NaCl and a beaker of AgNO3, and when you mix them together, you have a new volume. So what happens is every ion in those solutions becomes diluted, so their concentration goes down. Now, we'll do an example of this recalling C1V1 equals C2V2. And the principle of this, right, the background theory as a quick review, is that the number of moles don't change. So the moles of the concentrated solution are equal to the moles of the dilute solution. The only difference is the amount of solute. Of this solution changes, not the amount of solute. The volume of the solution changes, the moles do not, and we recall that moles are equal to concentration times volume. So if the moles stay the same and the volume changes, that means the concentration must change as well. So we'll look at examples of these. Going back to here. So determine the final concentration of each ion when these two solutions are mixed. So let's start with the reaction. We've got NaCl plus AgNO3 producing AgCl, which is a solid, plus NaNO3. And I've just left the aqueous signs out for now. So we're being asked to determine the final concentration of each ion when these two processes happen. So in this case, right, we're assuming that this is a saturated solution. So this, being an aqueous solution, will split up into its ions. So let's look at this. for sodium. To figure out its final concentration, we can say C1V1 equals C2V2. So because sodium has a subscript of 1, and we reviewed how to determine the ion concentration in part 1, its concentration will be the same as the molecule NaO3's concentration. Right, so we'll look here. Its initial concentration is based on this. So it's 0.1 moles per liter, and its volume is 25. We're trying to find its final concentration, and its final volume will be the total of the two, so 25 plus 25 milliliters, because they'll be mixed. So in this case, we're doubling the volume, which means the concentration will be halved, and you can check on that if you'd like to punch it in. So we'll do 0.1 times 25 divided by 50, which gives us 0.05 moles per liter, or half. So then we can do the exact same thing for NO3, right? C1V1 equals C2V2. So it was initially in the silver chloride. It's a 1-to-1 ratio, so its concentration is the same as the molecule. In this case, it was 0.01. And again, we started with 25 milliliters of that. We added the two together to get a total volume. So the final concentration of this, again, you punch this in, it will be half, 0.005 moles per liter. Right, so C2 represents the diluted concentration. Now, if you're wondering, well, why didn't we convert milliliters to liters in this case? And the reason is it's because we used milliliters on both sides. So if we had converted it, we would just apply a factor of 1,000. So it's not necessary in this equation. Volume can be in any units as long as it's the same on both sides, and concentration will be in moles per liter. All right. Now, assuming it's a saturated solution, we can do the same thing for the silver and the chlorine ions. If it wasn't saturated, then we could not, because some of it won't dissolve, right? But for chlorine, right, and here's where we can use some logic, and it's not a skill that needs to be practiced. Because that forms the solute, it'll form its own equilibrium, saturation, right, where it dissolves into its ions. So for chlorine, the chlorine is a 1-to-1 ratio. Again, it started off in the NaCl, so it has all the same numbers as the sodium ion. Okay, we'll just say it's the same as sodium in this case because they're 1-to-1. If they had different subscripts, we would have to go back and do the calculation. So its final concentration is also 0.5 moles per liter, assuming that it's saturated. We'll look at what happens when it's not saturated. And then for silver ions, the same thing, okay, because it's a 1-to-1. Okay. And if you're not sure, just remember C1V1 equals C2V2. And the ion concentration is equal to the subscript times the concentration of the molecule. So in this case, because the subscript is 1 for everything, the molecule concentration and the ion concentrations are the same. So that's a recall of dilution and precipitation and double displacement reactions. Now, before we conduct a reaction, we're going to bring back into the concept of Q. So we're going to predict before it even happens if a precipitate will form, right? And what we're essentially saying is the solution at equilibrium? Because if it's at equilibrium, no precipitate forms. Going back to what we learned earlier, to solve this, what we need to do is compare Q to K. Right? And under these conditions that we outlined before, if Q is less than K, right, it's before the equilibrium, so it's shift towards the products, which is the ions in this case. So if we write our reaction again, there's our solute, and there's its ions. So if it shifts towards the right, excuse me, then there's no products because it dissolved. Ions are forming. If Q and K are equal, there's no shift. Right? So it's at equilibrium, which is a saturated solution. therefore no precipitate forms. And if Q is larger than K when we calculate it, that means there's too much of the solute, so it'll shift towards the left and a precipitate will form. So that's the only time a precipitate will form when we're trying to predict that. So here's a complex example, right? And we'll break it down first into a roadmap. So we're being asked if these two solutions mix, we have one there, they're mixed. Determine if a precipitate will form. So to do this, we have to start off with reactions. Now, let's break it down into what the question's asking us. Determine if a precipitate will form. What we're being asked is it at equilibrium? That's essentially what that means. So to determine if something's at equilibrium, we need to compare Q and K. Well, to do that, Q is equal to the products over the reactants, and K is given us in the question as 3.6 times 10 to the negative 5. So to determine Q, the products and the reactants, we need a reaction and an equilibrium. But before that, what we need are ion concentrations in this case. They don't need to be at equilibrium because we don't know if it is. Once we have the ion concentrations, we can solve that. So we'll delete that there. Okay, so to determine the ion concentrations, we need to write a reaction. So we'll start off with that over here. So we're mixing calcium chloride, which is aqueous, sodium sulfate, which is also aqueous, and this is the reaction. So this is step 1. Okay, the double displacement reaction is not in equilibrium. And we will get calcium sulfate and sodium chloride, which is aqueous. And if we balance it, there should be a 2 in front of it. Now, because we're looking at the precipitate, and if it's going to form, which is describing equilibrium, we need to write a second equation. So, if that forms, it will dissolve into its ions, calcium and sulfate. So there's our equilibrium process that we needed. Okay. So now, to figure out the ion concentrations, we can either use an ice table, right, or we can use the dilution equation that we had, because what we're assuming is that this is at saturation. So we're not going to use ice here, right? We will use instead C1V1 equals C2V2, assuming that this is a saturated solution. So if we assume it's saturated, it'll give us our ion concentrations, which we can plug into Q. Then we can compare Q to K, and it'll tell us if it's above saturation or below. So let's look at this here. Right? So for Q, Q is equal to the concentration of calcium, and this is the solubility product, times the concentration of the sulfate ion. All right, now we'll use C1V1 equals C2V2 to determine the ion concentrations because they were mixed. So let's go down here. For calcium, C1V1 equals C2V2. We are looking for its final concentration, so we can plug it into our Q expression. Initially in the question, okay, if we look here, let's get a different color. Calcium chloride has that concentration and volume. So, because calcium has a coefficient of 1 in the equation, its concentration is the same as the molecule's concentration. So we can say 0.1, we're going to simplify this for calculations, times 100 milliliters. That's how much the initial solution was. We're trying to find the final solution, and the final volume is the addition of the two. So 100 plus 100 milliliters. Right, so when we solve for C2, okay, that's the concentration of these calcium ions at this point. So that's important. Now we'll say for the sulfate ion. All right, so this is just based on assuming that those solutions are at the saturated point. If they're past it, we'll interpret that when we compare it to K. So for sulfate, we're going to do the same thing. We need to use the diluted concentration because they've been mixed, and we'll note that here. Because they were mixed. These two ions aren't in the same solution until they become mixed. So if we look at that here, right, there's our dilution formula. Right, sulfate was there. Sulfate has an exponent of 1, sorry, a subscript of 1, not 4. That's just how many oxygen are there. Okay, don't forget it's a polyatomic ion. So there's 1 of it. So its concentration is 0.04, the same as the molecule it's in. 0.04. There was 100 milliliters of it. And we're ignoring significant digits for simplicity here. We're trying to find its diluted concentration. And the final volume is the addition of the two. So when we put that together, we're going to get 0.02 moles per liter of sulfate. So now these two represent the diluted ion concentrations that we can use for the Q expression. Right. So now down here we can say QSP from above equals the concentration of Ca2 plus times SO4. This is all 1-to-1. If it wasn't, we would want to remember to put our subscripts in. So we've got 0.05, 0.02. Right, we have no exponents there, so be sure to check what your actual equation is asking you for. Remember that this is just an example. Okay, so we've got our concentrations there. Hopefully you're trying to punch this in, and you'll get a value of 0.001 for Q. Okay, so that tells us, remember, the current ratio of products to reactants. We'll compare that to the expected equilibrium ratio and then determine what is going to happen. So we can say, therefore, QSP equals 0.001. If we scroll back up, K is given to us, 3.6 times 10 to the negative 5. So we can say in this case, Q is greater than K. And interpret that again. It means it's past equilibrium. So it will shift left, form reactants, which in this case means a precipitate will form, because the precipitate is the reaction of the equilibrium system. So that can be used to determine if a precipitate will or will not form when two solutions are mixed. There's applications in medicine, environmental chemistry, and the process is very straightforward and similar for all of them to determine what the reaction is, determine what the equilibrium process is, and then determine the diluted ion concentrations after they've been mixed. So that wraps up the first portion, which is part A and B. Part C will look at an extension of this and how different conditions can affect how much of something dissolves.